as soon as they hear that is why? Well, and there's a couple of whys. One of them is like, why is C++ not good enough for you? You know, everyone uses it. It's the industry standard. Isn't it great? And unfortunately, I do not have enough time in a 1-hour speech to list all the ways in which C++ causes terrible problems in game development. So we'll have to belay that for another time. But I think maybe enough of you at least vaguely know what I mean there. The other why that people might ask is, well, why do you have to go make a new language? There's so many languages. Isn't one of these new ones from the past couple decades good enough for you? And again, that could turn into a really long speech of, you know, listing out all these languages and like what I don't like about each one and so forth. And that would maybe get aggressive and start arguments and things. So I don't want to do it that way. But I want to sort of explain holistically why none of these newer programming languages I feel are up to the task. And I'm going to do that by talking about Photoshop for a bit. And this doesn't make sense yet, but it'll make sense eventually. So suppose I'm just going about my everyday game development life. Oh, I'm going to have problems here. Hold on. I didn't realize that in this presenter mode, I'm going to come out of presenter mode and start over. Sorry, because. All right, so do we see other things on the screen? Yes, we do. So suppose during my regular game development everyday life, I'm doing stuff like I've got a screenshot. I've installed Photoshop recently, and I want to look at a screenshot of the game. Someone reported a problem or something. So I double-click on the thing. 1, 2, 3, 4, 5, 6. It's about 7 seconds before I can actually see the image, right? And I'm a very sad person because I installed Photoshop, which for some reason was presumptuous enough to make it be the default handler for this image type, and I have to go like change that, and I grumble to myself and stuff. So that's really slow, and I'm going to talk about that for a bit. But there's an element of severe irony to this, which is that as soon as I double-click this thing, within 1 second, it draws an image, right? And it's a pretty high-resolution, interesting image. It's just not the image that I care about, right? So obviously, it's not hard to like start a process and draw an image on the screen in much less than 7 seconds or 8 seconds or whatever I counted. They just don't manage that. Now, I gave a speech a year ago that started the same way, where I was like, oh, I'm so disgruntled about Photoshop starting up slow. Of course, that was 2016. It's now 2017, and a new version of Photoshop has come out. And of course, what will align directly with my point in the next few slides, they've made it worse, right? And the great way in which they've made it worse is, say there's some operation that you maybe want to do once in a while, like create a new image, right? So I'm going to go to File, New, right? And that menu it probably takes about a second. It's hard for me to count 1 second, but it takes about a second to come up. And you might think like, oh, well, you know, it was just all these assets were cold or something. Maybe they come off the hard drive. It'll be faster next time. And it's like, well, let's test that out. Nope. Like every time, I'll use the keyboard shortcuts. File, New. See how fast I can type it versus how, right? Imagine if the people who programmed this were trying to make VR games. Like everybody would be vomiting everywhere all the time. So, well, what machine am I running on this on? It's actually a pretty fast machine. It's a Razer Blade laptop with a pretty high-end i7 in it. And, you know, you can talk about how fast the CPU is or the GPU is in some arbitrary measurement. And I'm going to discuss CPU speeds here. And I just want to say in advance that none of what I'm about to say is meant to be precise numbers or precise measurements. I'm making a general point, right? And the general point is that the CPU of this thing would have been approximately the fastest computer in the world when I was in college. Or, you know, the GPU would have been the fastest computer in the world in the year 2000 or thereabouts. Now, you might say, that's a really long time ago. This is the ancient Stone Age. And it's like, well, actually, Photoshop was released in 1990 before either of those dates. And Photoshop 6, which I used heavily during my earlier days in game development, is from the year 2000. And this is what it looks like. There's a screenshot of Photoshop 6. it's got all the same UI that Photoshop has today. It's got all these same control widgets, and it's got like our layers and channels and all that stuff, right? Today, the UI is a different color, but apart from that, it's essentially the same program. Now, I don't doubt that it has many more features, but you have to ask, like, how many more features are there, and what level of slowdown does that justify, right? And like I said, well, it was a long time ago, but you also have to keep in mind, even though 2000 seems like 17 years ago, we already had 3D games that look like this, multiplayer, hardware-accelerated action games like the year before that, right? So games were here. So it's not like the Stone Age when you could only draw like EGA pixels on the screen or something. This is relatively recent in terms of modern computers. In fact, I would even say that computers have not, unless you count like the mobile form factor or something, the way that we do things has not changed fundamentally since this time. So let's talk about how much faster computers have gotten. Here's a graph. It's spec FP, floating point performance, which is not necessarily completely relevant to application startup, but this is the graph that I found on Google Images, and we're making a general point here. So today we're on the upper right of this graph, where this is a logarithmic graph, so we're somewhere between 32 and 64. Let's call it 48. And if we're comparing to the year 2000, when Photoshop 6 came out, we're probably around 2. So 48 divided by 2 is 24. So single-threaded performance has gotten about 24 times faster since then. This laptop has 4 cores, though, or 8 if you count the hyperthreads. So Photoshop should be somewhere between 24 times and 192 times faster than essentially the same program was 17 years ago, right? Or if you say, hey, we should be able to utilize a GPU somehow. I don't exactly know how you use that for application startup, but I don't know why the application startup is so much work in the first place. So we could wonder about that for a while. But if you said we should be able to use the GPU, which is a monster machine, right, we should actually be able to get way more than 192x, right? And of course, this is all a simplification of ignoring RAM and hard drive speeds. This is an SSD, in case anyone is wondering. It's a fast SSD, but yeah. Now, my whole point is that it's not just Photoshop that has this problem. All modern software has this problem, right? Compilers are all really slow. Text editors are really slow. Operating system UIs, all the little windows that pop up, are frustratingly slow. Often, websites are really, really, really slow. Everything is slow. Signs are slow. So this cool sign over here, like, scrolls from right to left before every presentation. I don't know how many of you noticed, but it drops frames sometimes. And sometimes it stops and stutters like for half a second, like the garbage collector hit it or something, right? Why? There's not that many pixels here. I could probably count all the pixels in the time it'll take to give this talk. So I couldn't ask for a better proof to underline my point. So this is not exactly a new point, right? There's been this wisecrack in technical circles for at least as long as I've been around. And it's called Andy giveth and Bill taketh away. So on the left here is Andy Grove from Intel, and the idea is Intel keeps making faster and faster chips. And then Bill, on the right, makes slower and slower software, and they balance out, right? And over time, the experience stays about the same. And, this wisecrack is from the 90s probably, and it's still true, which is probably pretty amazing. Maybe it's from the 2000s. I don't know. Something. Now, the problem is if you ask Andy, what have you done for me lately? The answer is not really so much, right? So the amount that Andy giveth is decreasing over time. Here's a graph where, this is again a logarithmic graph. These triangles, orange on the top, are the transistor count. And according to Moore's law, the transistor count just keeps going up, right? But the blue and the green are performance-related numbers, right? So the blue is single-thread performance. It's an integer this time because it's a different graph. And then clock frequency is in green. You can see that that's basically completely flattened, right? So it's just to say that this is the trend over time. We can't really expect computers to be increasing in speed as fast as they used to. And we know that, right? Most of us in this room are familiar with this idea. But I've never paired that quite so directly with the issue of software getting slower. I'm not sure how strong the causative link is between these two things. Like, obviously, if the hardware is so much faster, that allows software to be slower, but like, does software have some kind of independent inertia where once CPUs really stop getting fast, software is just going to keep going, right? And just get slower and slower until it's completely intolerable. I'm not sure, because I'm not sure that most programmers even know what makes things slow anymore, right? And in general, though, the reason I've been talking about all this is to bring up this picture that there's some kind of general insanity happening broadly in the software development world, where things have gotten, let me see what my next slide is. Okay, see, I can't be in presenter mode, so I can't see the future. There's this general insanity of, there's all these people out there who are very sure, they have very strong ideas about how you're supposed to develop software, just about how it's supposed to be structured, right, and tested, and what the programmer is supposed to do, what the programmer's schedule is supposed to be like. And people are very convinced of the validity of these ideas and the correctness. But if you look at the software that's being produced, it gets worse and worse over time, right? Software today maybe has a little more functionality than it did in the 2000s, but because there's such a bigger market for consumer software, there's much bigger teams working on these things than there ever was. So you have to attribute some of the increased functionality to the increased team size. So like, what is really happening? Well, I don't know. Neither do all these people who are very strongly bought into these programming paradigms, but they think they know. And so there's some kind of insanity where the people just don't look at reality and see what's happening, but they continue to believe their beliefs. And it does a lot of damage, right? So the point is just, the point behind all that supercomputer stuff is just, if I took this installation of Photoshop that is on this computer today and traveled back to the Quake 3 days, which is not that long ago, you'd need something like the fastest computer in the world to run at an acceptable speed, right? Put in those terms, it's pretty freaky, I think. So to go back to my question of why I make a new programming language, and to broadly address this issue of why all these languages are not good enough, it's that they all make underlying assumptions about how you should program, right? They have ideas. The features of the language and the style of the language is designed to support certain styles of programming that most people have bought into. Certainly, most educational systems teaching programming have bought into. And they're designed according to these principles, and they're grounded in this insanity, and they're helping to perpetuate it in some way. And I want to avoid all that. So without naming names and without naming specific problems, there's a broad issue. Now, I want to come back to this graph as the second part of the why. And I want to make an analogy now. I'm not going to say anything about CPU speeds, but I got into games a little bit before the Quake 3 days. Actually, I started in 1996 professionally, and the Quake test for Quake 1 came out that shortly after I started, and then later that year, Quake 1 came out, and we didn't really know how to do a lot of stuff back then. Like, there were no 3D accelerators, so you had to know how to draw every pixel on the screen to somehow make a 3D scene, right? And that's really complicated, and there's lots of hard work to do there. We didn't know how to rotate objects in 3D space, right? We used like Euler angles, and things got messed up sometimes, and we were just like, well, put a hack in when that happens, or whatever. We didn't know what we were doing, but in the years after that, we made really tremendous progress. If you were to chart our progress in how what our technical advances are in building game engines, it would have a steep slope at the beginning. But I don't know how many people in the audience feel this way or have even thought about it, but I kind of feel like we don't really make advances in game engines very often anymore. I think it's undoubtable that games look better and better every year still, or every couple years, let's say. But I think in large part we are coasting on some of these other trends, like the faster machines. So a new generation of consoles comes out, we can make things look a little better just because it can throw more stuff at the screen. But we're not necessarily making advances in engine technology the way that we used to. And so I kind of wonder if we look like this blue dot curve, or the green dot curve even, and need to dislodge ourselves by sort of getting rid of some of the bottlenecks that we have, right? So if our tools are constraining our productivity, and we do a good job of revising those tools, that might buy us some more slope on one of these curves for a while at least. So the rest of this, I'm going to say some things pertaining to this programming language, and it's very tempting, because it's a language that I really care about and have personally designed and stuff, to try to turn this into a sales job where I list all the features and try to amaze you with it. And the problem with that is it's hard to go in depth on anything, and I'm sure you've already seen enough sales jobs at this conference, and it's only day one, right? Because that happens a lot in a situation like this. So I'm going to turn this more into a little bit of a progress report of what I'm working on, and that'll get very concrete and just show in specific terms what I'm doing. And then I'm going to go do a little bit of a dive into one feature. So the first thing that I will do is a demo of what I've been working on mostly for the past few months. It's a game because, if you make a programming language, you're making a lot of design decisions and you're justifying them in your mind, but unless that gets tested by reality, you don't know if your ideas are right. You don't know if they're working. You don't know if the features in the language could be better than they otherwise should be. So I figured, well, we should make and ship a game on this thing. So here's what I've got so far. And again, this is a work in progress. These are not final visuals. But it's a nice little grid-based game where I've got a guy who can run around. He can push blocks and stuff. This is like the one level that we have that actually looks good enough to show. It's not remotely final, but it actually looks like something. The rest of them look like programmer blocks and stuff. A lot of the work I've been doing lately is on the in-game editor, because I think for productivity it's really good to have that. So I can just hit F11 to pop back and forth between the editor and the game. I can load this scene in the editor, right? I can select stuff, and I've got like manipulator widgets. I can move my camera. I can I've got my nice, change the color of the thing, make it a weird green colored block. I don't know, let's copy and paste it, and I don't know, paste again. Let's keep selecting things and paste again. And you get, it's an editor, right? But it's got, I guess what I'm just trying to show is it's got a reasonable amount of functionality, which is a way of testing the language. I can, of course, I can go into the different fields of stuff. This is directly relevant to what we're going to talk about later, and I can just type in to change, I put the block on the guy. Let's put it above him, whatever. That's the general idea. So, and the other thing to say is there's a guy, Joshua Hulsman, who helps me working on the compiler, and he's doing, among other things, he's doing back-end work, but he's also making sure it's portable. So the whole compiler and that entire game that I showed also run on Linux right now. So this is a screenshot of a very obviously Linuxy machine running the same thing that I just showed. So Linuxy machine running the same thing that I just showed. So I don't really want to dwell too much on what the features of the engine are. It's a pretty reasonable engine, but it's not yet production quality. It renders in GL4 just because I didn't really want to learn a new API in the middle of doing all this other stuff while they're evolving, but I dislike OpenGL quite strongly, so we're going to probably switch it to something else by the end. But it's got light maps, shadow maps, and linear light rendering with nice tone mapping. The music and sound effects were being played in a separate thread in an audio mixer that plays PCM and will dynamically uncompress 80 PCM. And if you really want to compress something like the music, it'll page in Vorbis files and decompress them page by page, so you don't have to spend a lot of CPU decompressing all at once. And that decompression gets marshaled to another thread, right? Character animation we saw, and its serialization we'll talk about, et cetera. Oops. So there's enough features there that it's really not trivial. It's starting to be a really good test of the language. Now, I've been working on, I started the compiler project in late 2014, but it was a part-time project because we were kind of working on a game for a while. We shipped that game last year, and it's been about exactly 1 year since I've been working on the compiler plus this game as my actual full-time project. All the features in the engine, they're a lot further along, probably, than they would be if I was just like a guy who started out with an empty file. And that's because I pulled a lot of them from the witness, and many of those pieces came from earlier game engines, which means they're pretty far along in terms of functionality and level of development. I did not do machine automated language-to-language translation on these. I would paste the C++ into a new file and retype it by hand for several reasons. One, because that gives you a better quality resulting code. Two, it forces me to be observing at every time, how easy is it to express this thing in this other language, right? Am I having problems? Are things getting better? And then the last reason is, honestly, the code kind of needed some refactorings even before leaving C++, so it was good to do that. Now, at some point, when the compiler's ready, we're going to give it away, open source, with no, a totally free license on it, usable for any purpose. And the same goes for the actual engine, because I think when you see a new language, you want something better than like a hello world program. So whatever this evolve into is going to be part of the initial release. And the good thing about that is it helps keep it real with the standard library, right? Because one of the problems with the standard library for C++ and whatever is it's mostly full of stuff that you don't really directly care about. Like, you have to somehow make a connection between what you want to do and like what eventually the C++ standard library will help you with, right? And this standard library will have that kind of deeper stuff, but it'll also have like, oh, you can open a window, right? Play sound and SDL kind of things, so that you don't have to. So there's a high-quality standard version of all that stuff. The game that's been built so far has about 25 hours of gameplay, single player. It's not polished yet, and most of the levels look like programmer art slabs, but it's there, so it's non-trivial. I don't want to show the rest because we don't have time, and I don't want to actually announce the game. Okay, so let's talk about the language and what I've been having fun with. And the number one thing is compilation speed. I really like how fast it compiles now. So let me just clear the screen. And I'm going to hit F7, and when I do that, oh, the text is kind of small, but when I do that, it'll paste a thing to do the compile. So F7, boom. So that was a full rebuild of the game. It's about 54,000, 55,000 lines of code. That's including blank lines and comments. It took about 0.8 seconds, which is actually kind of slow, because Photoshop evicted all our files from the Windows cache. So I'm going to hit it again. That time it was 0.5 seconds, because we're all cached. And so, that's about, for this size of program, it's about 0.5 seconds to compile once you're in your working loop. So that's about 104,000 lines of code per second, with none of the complications that come from incremental builds. Let's not go into it, but I've had much grief due to incremental builds, right? And the thing to say about this is a compiler in progress. It's not even optimized yet. Like, I've spent maybe 2 to 4 days total in the past year making it go fast, which by the standards of game engine optimization, that is nothing. So first of all, this number is going to go down. I mean, the program size will certainly get bigger, but also this number is going to go down. So we'll see where it ends up. Now, the thing to say is almost 1/3 of that total time is just link.exe running, and we don't actually need that. So what we do right now is we have a backend that outputs x64 instructions into one single .obj file, and then we pass that to link to generate an executable. And that takes 0.17 seconds out of the 0.52. If you were to subtract that, we would be more down to like 1/3 of a second instead of 1/2 of a second, and that's a big difference. So it's on the roadmap somewhere to replace link.exe, because an executable file actually isn't that different from an obj file. The main thing that ostensibly would be happening is linking of static libraries. Now, I don't know why linkers are so slow. And this, by the way, is the lowest number I could get after trying to minimize, whatever the object file is that you produce will have some varying amount of work for the linker to do. And I've been trying to minimize that amount of work, and we still end up with 0.17 seconds, which is ridiculous because one of the main jobs of the linker is to put addresses on pointers and stuff. And address space layout randomization has to redo all that when the process boots up anyway. So I don't even know what it's doing. It is not doing link time optimization because that's turned off. Okay. Now, I will also say that in that 0.5 seconds, we are doing way, way, way more than a C++ compiler. And I don't just mean language features. I mean in terms of actual computation work that the compiler is doing. And we're going to go through some examples next. Then the main thing I'm going to talk about, like I said, I wanted to focus on one specific feature. And I'm going to talk about compile time execution, because it does so much in so many different places in this programming language. And there are many other features that I could get rid of, and I would still sort of feel like it's the same language. If I got rid of this, it wouldn't be the same programming language anymore. What I mean by full here is many compilers have some limited set of expressions that they'll evaluate at compile time, right? So there's const exprs in C++, and languages like D or Rust or whatever try to expand and formalize in order to give you more versatility to be able to do stuff at compile time. My approach is to say, why are you doing that? Let's do everything at compile time. And by everything, I mean everything. So I have this favorite. Anyone who's seen the YouTube streams knows what I'm about to do, but this is my favorite demonstration of compile time execution. I'm going into, right now, this file called first, which this is actually the metaprogram that compiles and builds the main program, and we'll talk about that in a bit. But it's, it's about 600 lines, so it's substantial, but not like long. And I've got this Boolean at the top, and I'm going to change go bananas from false to true. And that will change what happens when, so I'm not going to run the game now. I'm going to hit F7, which compiles, right? So here I am compiling. And what happens is I've plugged in a bunch of extra code into my metaprogram that plays music and graphs it like on the screen because I was feeling cheeky. And it gives me a bunch of stats about like what the different procedures are, and I can have different ways of viewing it. Like, if I want to know what's taking up the most size in my executable, it's not exactly what I'm seeing, but it's highly correlated. I can sort of look at where these spikes are and stuff. So if I go here, this is also integrated with my editor, so I'm just making my editor view visible on the left of the screen, and if I want to say, oh, draw game view 3D, where is that? And I click on it and it pops open, right? So it's talking to Emacs client and stuff. All this is running in the compiler. So what's happening is that there's an intermediate representation for the programming language, like most languages have these days. And the compiler just knows how to run the intermediate representation. And so you can run any code. There's no limitations, right? So you could use a graphics library or talk over the network or do whatever that you would like to do. So that's an example just to show something that's at the heart of the language. So why would you want to do that? Well, it lets you simplify, first of all. There's many reasons you want to do it. Firstly, it lets you simplify a lot of things. So I don't need a make file, I don't need batch files, I don't need MS build configs or Visual Studio props files or anything, right? Because the entire recipe for doing anything of arbitrary sophistication is in one programming language, and it's in the good one that's very powerful that I use every day. It's not split across like 5 crappy programming languages that I don't really know that well and that are confusing, right? And so I get more code sharing, right? Like I can use stuff from the standard library or from my own personal library of stuff that I develop. There's no obscure broken corner systems like, oh, the build scripts fail sometime because some of them are written in Perl and we're not really experts in Perl, and the one guy who was like quit 6 months ago, that kind of situation. And it works on every platform. So when I go to Linux, I don't have to throw away my, my Visual Studio props file and build an equivalent, right? It just exactly the same code works on Linux. Exactly the same code will work on macOS or anything when we do that. So I want to give an example of a little bit what it looks like to do this stuff in regular code. So like, how do you say you're going to make a debug build if you're not using weird command line options and stuff? It's just, well, there's a struct that describes what the optimizations are going to be, and you fill out members of the struct. So you have code like this. It just says, hey, let's get what the current build options are. Let's set the name of the executable. Let's set the path to put the executable in. We're going to use the x64, that's the fast back end. We're going to set the optimization level to 0, and then we're going to apply those build options to the current workspace. And I can go and show you real fast. Build options, yeah, there they are. So it's just, the syntax is a little bit different from C++. The names go on the left. But it's basically the same idea. It's just a struct like anything else. And you're just calling procedures on it like anything else. And that is very nice when it comes down to it. Because again, you can have the code that figures this out doesn't have to be this simple. It can be arbitrarily complex. It can be things that you can't even express in Visual Studio macros. Well, I guess they're Turing complete, but not within reason, etc. Okay, now the general engine of this compiler, it's a job system, right? Much like you would have in a game engine. It's not the kind of compiler where the compiler itself is single-threaded and you have to run it like 10,000 times to compile your program, right? And then, if you ever wanted something to be fast, I don't think you would say, hey, we'll run it 10,000 times, start 10,000 processes, write out 10,000 binary files to disk, load those back in, and then put them together. That doesn't sound very fast, right? And so the model here is you just pull in all the source, right? Compile it, write out the output once. And if you're going to do that for one build, you can do that for several builds. So, right now you can do things like, I'm going to build, debug, and release at the same time, or whatever, because it's my continuous integration machine or something. Eventually, we don't have cross-compiling yet, but we will, and you'll be able to do that here as well. So what that looks like is just, where's my cursor? Yeah, so I say, hey, I'm going to create a workspace, where a workspace just means I'm compiling some individual target, like an executable or a library. I call proc here, which is passed in, and one example of proc would have just been this, right? So I'm just passing in a procedure that says, hey, set the options. And then I just set the path for where the source files are going to come from, and I add one source file, which is main here, and then main at the top of itself, via the text of the actual program, includes a bunch of other files, right? And that's how you just set something up to build. But of course, you can run arbitrary other code. You can do things like, in the same language, at compile time, you can do things like process and pack assets, right? Upload your game to Steam by copying the files into like an outgoing folder and stuff and running the Steam client or whatever. You can do anything you want. Now I'm going to talk about specific things that I do in the game that I showed that use this functionality. And how compile time execution dovetails with introspection, or what some languages call reflection. And the first part of this is the kind of introspection that maybe people who use dynamic languages are used to, which is being able to see what the types are in your program. But this is working in a completely compiled language. So what I'm about to show is, it's like the equivalent of C++ RTTI, except RTTI doesn't really tell you anything that you wanted to know. So I don't know why it's there. So let's go to here. I hope the text is big enough. So this is a struct that just defines a bunch of types. And each one of these is, it's a node. Well, let's just say each one of these is a struct that contains the information about any type that can exist in your program. And when you compile the program, it builds a table of all such types that are possible, right? And then at runtime, you can say, what is the type of some expression? And it'll return to you a pointer to one of these structs. And what do you get? Well, it's a pointer to this thing, type info. And that's got a type tag, and the type tag is one of these things, and these collectively represent every possible type in the program, well, compounded by recursion as follows, right? So if it's something simple like an integer or a float, you have very simple information like, is it signed, right? How big is it? If it's a pointer, then there's a pointer to a different type of info of, oh, this is what type this is a pointer to, right? If it's a procedure, well, here's the types of the arguments, and here's the types of the return value. We have multiple return values, so there's more than one. If it's a struct, here's the name of the struct, here's all the members, and so forth. Now, you can get all this information at compile time or runtime, and it lets you really do a lot in both cases. Let's show an example at runtime. I'm going to just start hacking my game here. So the thing that's playing that music and sound effects is, this guy's sound player, and I've got a pointer to that guy, and I'm just going to say print this. Well, let's put some new lines in there to space it out, and sound player, and the little double left shift looking thing is just that's a pointer dereference in this current syntax. By the way, the syntax of everything you're seeing is temporary. Did I say that? I'm focusing on semantics and expressive power in the language, and then at the end we're going to do a pass to revise syntax. So I don't really care what the operators look like. But anyway, this is saying basically dereference the pointer to sound player and print that. And just by typing that, right, whoops, let me turn off Go Bananas. I mean, we could wait for that to Yeah. All right. So just by typing that, now I'm going to run the program. Turn off the audio, I guess. Whoops. So now every frame, I'm printing out the state of the sound player. And because the print statement has access to this runtime type information, I can just print every field and every value very intelligently. I'm not making any attempt to format it nicely, but it's pretty interesting that like this is probably about half the usefulness of what a debugger gives you right now. And you can just do it, right? You just say print and then the thing. And of course, it's a more type-safe print than C++, because you don't have to specify the type in here because it knows what the type is. You just put % anytime you want to insert something. Let me take that out, because it's a weird thing to have laying around. Now, that is not some kind of special compiler power that's baked in, right? That's also the same way when I showed this earlier, like when I selected this rock and did stuff with it. That's how I know what the fields are, right? In games like The Witness and earlier, we had to do some really annoying things that involved, you know, macros and like manually registering members and stuff whenever you want to add something to a struct. And I really like not having to do that anymore, and it's less error prone. And you know, sometimes people put together systems where you try to parse a C++ header file, and like you know, there's invariably problems with that, like it doesn't understand everything correctly, or you know, it only lets you do a subset of things. So this lets you do everything because the compiler knows the final type of the thing, and it just tells you. So another nice thing that I can do, oh, actually, let's wait on that. So there's sort of two layers to this thing of how we use this type information. That part was sort of the runtime part, where I just printed things or ran that editor with the GUI. But there's a compile time section also, because as a game engine, I want to manipulate entities. How do I know what the entities are, right? Again, in previous games, we had to manually register those in some way, and here we don't. So what I'm going to do is click really fast to the metaprogram that, what was it called? Oh yeah. So here's a string. This is like a here string like you have in shell scripts. And it's meant to be put in print, and it looks like code, except it has % everywhere that we're going to insert something, right? And at compile time, after all the structs are done compiling, I call this routine, which has all these arrays of strings. And what those are is just, I'm going to add lines of code to each of those, and those are going to be concatenated into strings that get inserted into that previous string to make code that then gets compiled in a metaprogram way as if it were source of the original program. And so then what I do here is I search for all the entities in the game, and I make code to register them at startup in an appropriate array so that then the rest of the system knows about them, right? So this is pretty straightforward. It's like, hey, let's get the type table. The type table is an array of pointers of those type infos that I just showed. For everything in the table, well, if it's not a struct, we don't care about it, so ignore it and continue. Otherwise, we get the info struct by casting. If it's this thing called unknown entity, that's like some entity casting hack that we have. It's not a real thing we care about. Otherwise, if it's a subclass of entity, with that's just a helper function that navigates that type table to see what is connected to what. Then we just add it to some array of entity types, right? Then we sort the array by name, and then we iterate over everything, and we generate a bunch of this code. And rather than you know, try to fly through there to explain what all that does, I can just go here, because when you generate code through programmatic means, you have the option to save it to a file for debugging purposes, right? So I've done that, and so here's where the entities start. Well, there's 30 entity types, and here's the names of all of them. And here's, you know, if you want to allocate entities, it's good to allocate entities of the same size next to each other and things of the same type with the same size. So, and iterating over them as well, you're going to have more memory locality if you do that. So I just spew out a ton of these storage structures, which would be annoying and tedious to do manually, but I just do it. And then there's a bunch of other dumb functions that I do, setting up the default state for every entity so I can like diff it and undo it and stuff. Yeah, that's enough on that. Oh, well, let's show one more thing. And just, Of course, you can navigate those data structures to generate multiple representations. So here, for that rock I selected, here's the actual file that goes into source control for that level. It's one file per entity, and it's text because that lets multiple people edit things, and the source control system can usually merge them, which is less true if you pack all your entities into one file. We write the field names here, but they're not used for loading because that would make loading slow. You don't want to look up names, right, at startup time. For any version of this entity, I know what all the fields are and where they live. So, oh yeah, this is an experiment. So just to show how nice this makes things, I'm going to make a new entity type, right? I'm going to make something called reboot developer, I guess, or that's a struct. It's a base class of entity, and this is how we do that. It's just struct inclusion. It doesn't have weird OO stuff. And we'll give it a couple of fields, like hello is 33 and whatever is 111, right? So that's it. So now there's a new entity in my game if I didn't screw something up. So I can compile, I can run, and I'll pop open the editor, and I can go here and press R, and there's a reboot developer, right? And so I can instantiate that guy, and it's got these fields. They're gray. You can't see them very well because they match the default value, but like if I click on it, it'll get brighter, right? And I can change those and whatever. I forgot to mention all this metadata also is how undo happens. So not only can I cut and paste things, but like I can undo and redo and all that good stuff. So those of you guys who have done this stuff in C++ know what a pain in the butt it is, but it's actually very easy to automate here. Even in past games, we would do macros to try and help it be easier, but you still had to do things in multiple places, and it kind of sucks. Now, in the same way, so that's an analog to what you get in a lot of dynamic languages, but there's actually a more powerful thing we can do as well, which is that we get equivalent data structures for the entire text of our program after it's been parsed and type checked, and we can inspect that in the same way that we just inspected the type information, right? So, and that's how this whole thing worked, right? That's how I know what the different procedures are and what they're called and how big they are, is because I actually can look at the syntax tree from my own user-level code at compile time. Very powerful. So let's look at what those structs are. I want to look at this. So again, there's sort of a base class struct thing, and it's got this enum that declares what all the different types of things can be in the language. So if there's a while loop or an if statement or an identifier or return statement, like all that kind of stuff is here, and as you navigate the tree for your program, you'll see each one. Now, this is only available at compile time because it seems like overkill to pack it into your executable at runtime. It's a lot of information. I suppose you could serialize it if you wanted that information at runtime, but I see it as a mostly compile time thing. So as some examples, for every single procedure call in your program, you get one of these procedure call nodes that says what the expression is. Maybe it's a simple identifier. Maybe if it's a pointer dereference, it's something much more complicated. What the arguments are, right? If it's a return statement, what the return values are. If it's a while loop, here's the condition and the block of statements for everything. And so that's one of the things I meant before when I said that this does way more work than a C++ compiler gives you, because it's giving you, it's passing to your program in an organized way all of this information for everything in the program. It blows anything in C++ out of the water, I'll say that. So here's what that looks like. This is a slightly simplified version for the purposes of fitting on a slide, but in our metaprogram, we go into some loop. It's just a common message handling loop, like most people have done many times. So I just say, hey, there's some message. We're calling compile wait for message, and we get that back. If it returns null, we're done. So we break out of the loop. If it's a message that code has been type checked and is ready to be inspected, and then we cast up to that message type, and we look at a declaration. And if it's not a procedure, again, we'll ignore it, because whatever code I'm writing now cares about procedures. Otherwise, let's do something with the message. Now, an example of what you might do with the message is, say, that's not contrived like the Go Bananas thing. Like, maybe I have console commands in my game, and I want to register new ones, right? Well, I can tag any procedure with a note here that says register command, right? And that's not a thing that the compiler knows about. That's just a user-level thing. And then in my metaprogram, I can do things like, well, let's look all the notes on the declaration. If there's a register command, do a certain thing, right? If there's key map stuff, do a certain other thing. And then, for some reason, I switched from commands to key maps when I made the slide. But then, similarly, after you've collected all the information, you then can sort of generate a procedure. Here's the declaration of the new procedure. And then for every key map proc that I want to register, because I found a handler for it in the code, I just generate a line of code that adds that at startup, and then I end the procedure, right? And so, again, I can do a fun example of that. So I can make a command, like squaring numbers is an easy thing. So I could say command square is some procedure that takes an integer, right? And I'm going to say there's some string. sprint is like a print statement that allocates space for the result. I'm going to say the square of whatever is whatever, and n times n, right? And then that's allocated, so I'm not going to forget to free it. And then I'm going to say, what is it called? Console, add to history s, right? Oh, and then don't forget the register command. So that's all I need to do if I didn't screw it up to create a console command. So we're compiling, we're running, and now I say, whoops, F1, square. Well, you didn't pass the argument because it knows it needs an argument. Square 5, square, negative 99, right? And because we have full type information, this can be very sophisticated, right? So that knew that this required an argument, but I can say, well, the default is 11, right? And then we run again, and I can still say square 9, and it gets it, and then I say square with no argument, and it squares 11, right? I can change it to some other type, 11.5, and same thing, right? So square with no argument, square 3, square 1, 2, 3. It's going to complain about too many arguments now, right? So this is very nice when you're doing this kind of work. I like it. I guess that's all I have to say about that. Yeah. Okay, so in addition to all this, there's a bunch of stuff I don't have time to show. You can do arbitrary analysis, correctness checks on your code, house rules. So one house rule that I have in my game engines is, there's entities, and when you tell them to destroy so that we can avoid problems, they get tagged as destroyed, but then we don't free them till the end of the frame. But then we do free them, so you're not allowed to hold like an entity pointer across a frame boundary. And the way that you enforce that, you can tell people, but then the new guy shows up, and you tell him, and he's like, yeah, and then a year later, he's eventually doing entity programming, and he forgets, right? But you can have an analysis that says, hey, you have an entity pointer on this one struct, and it's not whitelisted as the things that are allowed to have entity pointers, right? You can do an arbitrary amount of automated code review with this kind of compile time execution. Also, there's a YouTube video where for kicks I did, there's an automotive coding standard called MISRA where they have all sorts of stuff like you're not allowed to have indirectly recursive functions, and I did some checks for that. It was pretty fun. Not really, but. And then you can also modify code. So those data structures that I showed, you can actually modify them and resubmit them. So you can insert new things, you can move things around, and that's fun. Again, no time to show it, but there is a demo on YouTube. And that's like one feature out of the many, many fun and useful features. Now, I don't want to oversell it, right? It's not done, so I'm not giving out the source of this yet. Hopefully soon. I don't want to put a date on it. But I have to say that I'm just having a lot more fun programming, even though I'm programming in an immature language and bugs come up once in a while in the compiler, which, we know compiler bugs are not the most fun thing, but I'm having so much more fun programming because, I have hope that I'm not going to be shackled to this ball and chain of C++ forever. So that is, the last thing to say is if anyone has questions or comments about this, you can email to this address. It's not a mailing list. This is like an address that I use just to read feedback about it. I don't always reply because sometimes I get a lot of mail, but if you're interested, you can contact me there. We started late. I don't know if we have time for questions. Do we? Yes? Okay, so questions, yeah. Yes. Okay. So the question is about rearranging data structures for performance and stuff. Yes, that is a heavy concern in terms of the design of the language. I will say that I don't know if we're going to be able to completely prove it out to the degree that AAA games would need, because this game is designed to be a little simpler, right? It's like we're building our way up. A lot of features. So there's, for example, on YouTube, I have a demo of an SOA feature where you can tag a struct as struct of arrays, and anytime you make an array of it, it does the SOA thing, right? And that's not doesn't have. It's not as fully featured as I would like in the end. And in fact, I think there's a super version of that that's going to be better. And we're going to do that. But like to really know if that's really working, it's like you need to be shipping a PS4 game that barely fits and stuff. And so I don't think this game is that game because it's designed, the top-down view especially is designed, I actually had a slide about this. You know, the top-down view is designed so that there's only a constrained amount of stuff on the screen at once, right? I mean, it's very different from like this kind of game, which we just got done doing, where you can see across the whole. This requires a lot more work. And so, yes is the answer. I care very much about that. And that's the kind of thing I meant at the beginning when I was talking about how a lot of these programming languages make bad assumptions. So like a lot of the assumptions behind C++ encourage you, for example, to heap allocate things or to have them be separate. And I think that's pernicious, right? So I'm designing for that. I'm just saying that it'll take a while to test if that really works. But we'll see, and we'll take action if it doesn't work as well as I would like. Because I think there's just so much room there. There's so many, like think about all the things you would do if you really could make code in C++ as fast as possible. You would like annihilate all the abstractions and do something that's completely unmaintainable and whatever, right? And we never go that far. But like if you could like start with the high level code and like automate that kind of transformation, it might become feasible. So that's the kind of thing I'm thinking about. Yeah.
Hi, I have a question about your plans about pushing this language into the world and making it work with the existing code. Is that a consideration for you? Because it would help if people could work with their existing code bases and not rewrite everything from scratch.
It is a consideration, and I'm going to sort of cross those bridges as I come to them. You know, right now you can call out to C libraries, right? That's pretty straightforward. So, and we do that for some things. So, for example, I don't know if you know the STB C header file libraries, but we use STB image for loading textures and stuff like that. And then, you know, C++ is a little more involved, and it depends on how far we want to take that. I mean, I really don't know. We have to see. I think it would be a mistake to like come up with a plan for that before looking in depth at what people actually need, right? And so we're going to see. You know, people have these engine structures lately, like the Unreal Engine's doing, where things are broken into a bunch of DLLs, and you sort of can. Each DLL could sort of be its own universe as long as it knows how to talk to everybody else. So that kind of structure might be a way that this gets into bigger engines. But on the other hand, my plan is to make this so good that people want to use it anyway. So, I mean, it's not, you know, it's not practical for a AAA company to turn on a dime and throw away 2 decades worth of code and say, hey, we're going to use a new language. And I don't really expect that. But, you know, if people are like enjoying playing with something at home on their own time, and then there's a meeting one day and they're like, why don't we write our new tools in this? Because the tools are disconnected from the game and it would be save productivity and stuff. Like some studios did that with C#. And I think like over time things become adopted, and they also get gradually tested. And that's important. I don't want to try to convince people to use this stuff because it is so radically departed from a lot of other languages. I don't want to convince people to use it before it's tested either, right? I want a sort of a slow rollout so that we know for sure that everything is the best that it can be. In the front. Oh, well, he's already given the mic. Never mind. Okay, go.
Hello. As I understood, the language can generate itself can it do runtime, like just-in-time compilation?
I am not a fan of just-in-time compilation. So you could have given a very ostensibly computer science-y argument for it like 20 years ago or even more when Java was starting, which is like, at runtime, you know more about the state of going into your procedure than you do at compile time, so you can generate more efficient code. But that didn't really turn out to be true, especially when you optimize things the way that we optimize things, right? Like, regular programmers do not understand what game engine programmers do to make things go fast. It's completely different worlds. So, I'm not a big fan of JIT. I like predictable startups and predictable runtimes, and I like not dropping frames, like the sign. Maybe the sign was jitting, like, I don't know, right? Like, that's one of the things I don't like about OpenGL is it'll decide to compile a shader, right, in the middle of while you're walking around, and you're like, I didn't want you to do that. So I don't want to get into a big argument about JIT, because I know there are people who are like JIT evangelists who will defend it. So having said everything that I just said, that it's not my priority and all that, you can do it already. Like, you can compile to a DLL and then call out to the DLL. Yeah. That sounds like JIT to me. I guess I don't understand the difference. I mean, so you're asking, if I repeat the question to make sure I understand, you're asking, at runtime, can you? Yeah, you certainly could. I don't think I'll be doing that on the PlayStation 4, right? But like as part of a tool system or something, yeah, maybe. Do we want to get someone on this side? Yeah, in front.
Hey, I just want to say that the sign jittering was annoying me for the whole day, so I'm glad that someone else noticed that. So this might be too early to ask about, but what are you doing about optimization? Are you planning to pass it to one of the existing to-do standard, like common sub-expression, and all the things have been optimized for years in C++? Are you doing that kind of thing, or are you planning to use something external for that?
So there's a short-term plan and a long-term plan. The short-term plan is already in place and will be improved over time, which is that we have a backend that I didn't show you guys that compiles to LLVM, right? And so, you know, there's some nuances. You know, you can't just plug into LLVM and then get the best code in the universe. Like, there's nuances of like how to hint it and get it to do the right thing. But it's already, you know, it's all right. It takes longer to do that. And things are still interactive, you know, without that. So the code generation that I showed today, like when I hit F7 and it compiles in half a second, that is the maximum dumb emit x86 instruction. It doesn't even use registers. Like, it loads something into A from memory, does plus, and then stores it back in memory, right? And it still runs kind of okay. So there's going to be work to do there that's not even like optimization, but like, let's also make the dumb thing faster so that the envelope of how useful it is increases, right? Because at some point, it'll get too slow and you want to start turning on optimizations. Now, in the long term, though, so like I said, there's all sorts of ideas that I don't think are good that like everybody has bought into. And one idea that's not good that all compilers have bought into, as far as I can tell, maybe not the Go compiler, maybe even that one, I don't know. Compilers have this idea that you want to be dumb on the front end and smart on the back end, right? Because otherwise you get into like redundant optimizations. You could have common sub-expression elimination in your tree format, but then you also have to notice duplicate values in your intermediate representation or in machine code. So if you just ignore the sub-expression elimination, you'll like catch those eventually, or whatever, or if you don't try that hard, right? The problem with that is that your compiler does more work, right? Because you're generating all this code, and then you have to do all this optimization to get back to where you would be if you just hadn't generated all the dumb code. So part of the long-term plan is to put more front smarts in the front end than people typically do as well. We'll see how that goes. But we're already pretty unconventional in the front end. Like I said, it's a job system compiler, which like I don't know others of those. Not all the phases are jobbed, so like lexing and parsing is jobbed. Semantic analysis is not yet. That's the hard one. It's maybe not that hard. We'll see. I'm mumbling now, so that means that's the end of the answer. Do we have more time?
We can do one more question.
One more. Who's got a really, okay, in the red.
Hello.
Hey.
You talked about Photoshop a lot and how it got slow over
Yeah.
time. Are you seriously implying that if that program is rewritten in this new language, it will get faster?
What was the last part of the question?
Are you implying that if Photoshop is rewritten in this new language, it will get faster?
Written in which?
Rewritten in your language.
Oh, no. So the question is, am I implying that if Photoshop was written in my language, it would get faster? I don't think so, because the problem there that I'm talking about in the beginning is not exactly a language feature problem. It is a little bit, because like I was saying, C++ encourages you to heap allocate stuff, right? It encourages you to think of every piece of data as an isolated, abstracted thing, and we all know that everything that's fast does big groups of stuff at a time, right? So there is an interaction with language features there, but I think the real problem is how programmers think about writing software, right? They think that abstractions are okay everywhere. They think that adding abstractions is good. It's a little bit good, but it has flip sides, and they don't consider the costs. And they also, there's this idea of a zero-cost abstraction, where it's just like a macro or something, and it's free. Zero-cost abstractions are really not free for the same reason, because they control the way you think about the program and will make you think about something that's slow. So if the same programmers came and used this language and they programmed the same way, it would be about as slow, probably, right? But what I'm saying is the design of this language is to allow people who know how to make things fast to do the things that they want to do. It's not going to magically make a different way of programming faster. So, yeah. I think that's it. So thank you, everybody, for your time. And like I said, you could email me there.
you.